Howdy. This video is on the relationship between structural chemistry and acid strength. Specifically, we'll talk about Bronsted-Lowry acids and we'll talk about Lewis acids. Now, it's important because acids are important compounds and you should be able to understand why some acids are stronger than other acids. Now, after watching this video, you should be able to identify how Bronsted acids and bases react, identify the characteristics that make a good Bronsted acid. Well, actually, it's kind of cool. We'll see that there's only 3 of them that we need to consider. You should be able to put a list of acids in order of increasing strength based on their structural chemistry. You should identify how Lewis acids and base react. Identify if something is behaving like a Bronsted acid or base or a Lewis acid or base. In terms of Bronsted acids, if you think about them, they lose hydrogen ions. And so the more polar the HX bond, where X is a different element, the stronger the acid. Again, the Bronsted acid is losing a hydrogen ion, not the hydrogen atom, but the hydrogen ion. And so the HX bond has to be polar, so it loses the hydrogen ion. And so the more polar the bond, the stronger the acid. Now it's losing the ion, and so the weaker the bond, the stronger the acid. And so the first 2 criteria that we're looking at are really pretty straightforward. The more polar the bond and the weaker the bond, the stronger the acid. Now the final one is that the more stable the conjugate base, the stronger the acid. Now the conjugate base is going to be in the products. The more stable the products, the more products you'll have at equilibrium, and hence the stronger the acid. Now if we look at the second row of the periodic table, you have carbon, nitrogen, oxygen, and fluorine. Now if we look at the compounds with hydrogen, and we look at the difference electronegativity. Remember, the difference electronegativity can be used to determine the polarity of the bond, not the polarity of the molecule. CH4 is symmetric, so it's not polar, but the difference electronegativity gives you the polarity of the bond. The bigger the difference, and the difference electronegativity is symbolized by the delta chi, the more polar the bond. Now, of these 4, HF is going to have the most polar bond, 1.8. And it has the largest Ka. Remember, Ka, the bigger the Ka, the stronger the acid. Methane, carbon, hydrogen, has the least polar bond, and it's the least acidic. And so the more polar the bond, the more acidic. And again, if you think about it's losing a hydrogen ion, that bond has to be polar. It's also interesting, ammonia is actually a stronger acid than methane. Ammonia is also a stronger base than methane. And so you can have something that's a stronger acid and a stronger base than something else. And maybe it's just because the methane is really stable, it's not going to be very reactive, and the ammonia is more reactive both as an acid and as a base. You should also remember from conjugate relationships, the stronger the acid, the weaker the conjugate base. And so if you want to go from the acid to the conjugate base, you just remove the hydrogen ion. And so the conjugate base of HF is F minus. The conjugate base of CH4 would be CH3 minus. Now I mentioned the stronger the acid, the weaker the conjugate base. And so HF is the strongest acid of these 4. And so that means CH3 minus is going to be the strongest base. F minus is going to be the weakest base of these. Now, if you look down the halogen row, so you have fluorine, chlorine, bromine, and iodine, and remember, as you go down the periodic table, the atoms get bigger. You should also remember that there are 2 criteria for bond strength. One is number of electrons being shared, and the other is the size of the atoms. Now, for HF, HCl, HBr, and HI, they're all forming just single bonds, and so they're all just sharing 2 electrons. But the iodine is bigger than bromine, which is bigger than chlorine, which is bigger than fluorine. And so the iodine and hydrogen are farther apart, and so it's going to be a weaker bond. HF, the fluorine is much smaller, and so it can get closer to hydrogen, and it's going to have a stronger bond. And so the bond strength for HI is 299, HBr is 366, HCl 432, and HF is 565. Now, the weaker the bond, the stronger the bond. And so these 3 we consider, HCl, HBr, HI, we consider as strong acids. We consider that they completely dissociate. HF, we consider a weak acid. Its Ka is 10 to the minus 4th. And the reason that HF is a weak acid is that the HF bond is too strong. And again, remember the conjugate relationships. The stronger the acid, the weaker the conjugate base. And so the chloride, bromide, and iodide we actually consider as neutral. They're not really basic. They're called conjugate bases because we took an acid and removed the hydrogen ion. The fluoride ion is basic. It's got a Kb of 1.6 times 10 to the minus 11th. And so the stronger the acid, the more polar the bond, the stronger the acid. The weaker bond, the stronger the acid. Now we can combine these two. As we go down to the right, we're going to a stronger acid. Because as we go from left to right, the bond is getting more polar. Remember, for electronegativity, as you go up and to the right, electronegativity increases. So left to right, the bonds are more polar. Top to down, the bonds are weaker. And so HCl is a strong acid. Methane is not really acidic at all. Now, a special type of acid that we should talk about is called oxoacid. And so oxoacid typically have a center atom, and then they're bounded to oxygen, and then you have hydrogen bound to the oxygen. Now, this is phosphorus acid. It's also got a hydrogen on the phosphorus. And one important thing to mention is that only the hydrogen bound to the oxygen are actually acidic. So phosphorus acid has two acidic hydrogens. They're both bound to the oxygen. The one bound to the phosphorus is not acidic. Now, if we think about that criteria, the more polar the bond, the better the acid. The weaker the bond, the better the acid. We can actually come up with, we can adapt that to the oxoacids. And so the more oxygen, actually, the weaker the bond. And the way that we can think about it is the more oxygen bound to that center atom, the more positive the oxidation state for that center atom. Remember, the oxidation state, oxidation number are synonyms. I use them interchangeably. And oxidation number is the charge the atom would have if the bonds were purely ionic. And so if you have a very positive oxidation state, what's going to happen is the chlorine is going to grab electron density, weakening that OH bond. And so if you're looking at the same center atom, the more oxygen, the stronger the acid. Now, typically we don't compare when you have different center atoms and different number of oxygen, only when you have the same center atom and looking at the different number of oxygen. And so more oxygen, stronger the acid. And for this series, HClO3, HClO4, perchloric and chloric acids are strong acids. Hypochlorous and chlorous acids are weak acids. If we look at HNO2 nitrous, HNO3 nitric, the nitric is a strong acid, nitrous is a weak acid. H2SO4 sulfurous, H2SO3 sulfurous, H2SO4 sulfuric. The sulfuric is a strong acid, the sulfurous is a weak acid. Now again, you have to make sure that you don't compare different number of oxygen and different number of center atoms at the same time. Notice that nitric acid, strong acid, has 3 oxygens. Sulfurous acid, a weak acid, even though it has 3 oxygen. But do notice that, more oxygen, the stronger the acid. And so that's how you can remember that nitric is a strong acid, while nitrous is a weak acid. Sulfuric is a strong acid. Sulfurous is a weak acid. And so the more oxygen, the more electron density is going to pull from that oxygen-hydrogen bond, making that bond weaker and more polar. We can also look at the effect of the center atom. The more electronegative that center atom, the stronger the acid. And so the chlorine has electronegativity 3.2, bromine is 3, iodine is 2.7. And so the chlorine is the most electronegative of these 3. And so it's going to be the stronger acid of those 3. Now again, notice that we're looking at the same number of oxygen, and so we don't compare different center atoms and different number of oxygens. Now we can also take these concepts and think about when we have small, highly charged metal atoms in water. And so say we have, iron 3+. Now, when in water, it's going to be surrounded by the oxygen part of the water molecule. Now, if it's really small and highly charged, what's going to happen is, again, it's grabbing electron density, and it's going to weaken that oxygen-hydrogen bond, and you actually will form a hydronium ion. It's kind of interesting. You're having something affect electron density of a bond a couple bonds away. And the iron and oxygen actually don't form a bond. That's an electrostatic interaction. And so we can actually form Kas, or look at Kas for different metal ions in water. So iron 3+, chromium 3+, aluminum 3+, have distantly strong Kas, 3.5 times 10 - 3. The iron Ka is actually bigger than the Ka for, say, HF. Now, if you look at iron 2+, notice that's 1.3 times 10 - 6, and copper 2+ is 3.2 times 10 - 8. And so the more positive that charge, the larger the Ka, the more electron density that's going to grab. And so we've seen that the more polar the bond, HX bond, the stronger the acid. The weaker the HX bond, the stronger the acid. I mentioned that the more stable the conjugate base, the stronger the acid, because the conjugate base is a product. And so for the oxoacids, typically their conjugate bases are going to form resonant structures, or have resonant structures. And when you have resonant structures, compounds with resonant structures are a little bit more stable than expected. That's because you have some delocalization of the electrons. And so that's why a lot of those oxoacids can be strong acids, because you're going to get those resonant structures. Now, if you have the COOH group, that's called a carboxylic group. And so it corresponds to this carbon, oxygen, oxygen, hydrogen. And so it's a little confusing. It has COOH in order, but actually the carbon is bound to both oxygens. Now, this is organic acid. They're all weak acids. And one way you can understand why these are weak acids is that this oxygen will actually, because it's very electronegative, will weaken this oxygen-hydrogen bond. And so this is 1, 2, 3. And so oxygen is actually affecting a bond 3 bonds away. The other way we can think about it is that the conjugate base is going to have a resonant structure, right? We can't put the double bond there or there. And so the conjugate base is going to be a little bit extra stable. And so it's a product. And so that is why the carboxylic acid is going to be a little bit stronger than you might expect otherwise. And so again, resonant structures, the actual structure is going to be an average over the resonant structures. And the resonant structure, we can put a double bond there or there. In actuality, each of these bonds have a bond order of 1.5. Now, I mentioned that this oxygen is grabbing some electron density away from that OH bond, making it weaker, which is why carboxylic acids are acidic, where alcohols really aren't very acidic at all. You can also put a chlorine, substitute a chlorine for these hydrogens, and even though it's 1, 2, 3, 4 bonds away, it also, a chlorine here, can grab electron density away from that, making it even weaker. And so for acetic acid, no chlorines, you have a Ka of 1.8 times 10 - 5. If I change one of these hydrogens to a chlorine, my Ka goes to 1.4 times 10 - 3. If I change 2 of these hydrogens to chlorine, then my Ka becomes 3.2 times 10 - 2. And if I make all 3 of these chlorine, then my Ka goes to 2 times 10 - 1. But again, it's really kind of fascinating. You're substituting the hydrogen with something more electronegative, like the chlorine. It's going to draw electron density away, weakening that bond, making it a stronger acid. And so the more polar the HX bond, the weaker the HX bond, the stronger the acid. The more stable the conjugate base, the stronger the acid. Now, this is for Bronsted-Lowry acids, right? Bronsted-Lowry says the acid donates hydrogen ions. And so that's what we're talking about. Now, Lewis says acids accept electron pairs, bases donate electron pairs. Now, I want to make sure to specify that, for both Bronsted-Lowry theory and Lewis theory, you're looking at how is something behaving in a reaction. Arrhenius theory is just, you add it to water, what's happening. Bronsted-Lowry theory and Lewis theory, they're consistent. All Bronsted-Lowry acids are also Lewis acids. But Lewis theory is a little bit more general. You can have something that's a Lewis acid that is not a Bronsted acid. And so if we look at this reaction, we have ammonia with water. We can describe it using Bronsted-Lowry theory. And what we'll see is that the water is going to lose its hydrogen ion. And so the water is behaving like an acid. The ammonia is gaining that hydrogen ion. And so the ammonia is behaving like a base.
Ammonia is a base in the Bronsted sense because it acts as a proton acceptor. For example, It accepts a proton from a water molecule to form the ammonium ion and hydroxide ion.
Now, we can also use Lewis theory to explain exactly the same reaction. Right, so the ammonia grabs the hydrogen ion, but the way it does that is by donating its electron pair. And so because it's donating electron pair, we'd say that ammonia is behaving like a Lewis base. Now, because the water is accepting electron pair, we'd say that the water is acting like a Lewis acid.
In the Lewis acid-base theory, the emphasis is on the electron pair. Ammonia is a base because it acts as an electron pair donor toward the proton. The proton is an acid because it acts as an electron pair acceptor.
And so same exact reaction, we can explain both with Bronsted-Lowry theory and Lewis theory. Now again, all Bronsted-Lowry acids are Lewis acids, all Bronsted-Lowry bases are Lewis bases. And again, the way of thinking about it is like ammonia is a base because it's grabbing the hydrogen ion, but it's doing that by donating its electron pair. Now, because Lewis theory is more general, you can have a Lewis acid that is not a Bronsted acid. And so if we look at this reaction, here we have ammonia with BF3. And so ammonia has that nice lone pair. It can donate to form a bond between the nitrogen and bromine. Now, because there's no transfer of hydrogen ions, we cannot use Bronsted-Lowry theory to actually describe that reaction, but we can use Lewis theory because we're talking about a lone pair of electrons.
Lewis acid-base theory is more general than Bronsted theory because it applies to systems that do not involve protons. For example, ammonia acts as an electron pair donor toward boron trifluoride, a molecule that has a vacant 2p orbital.
And so previously we talked a little bit about metal ion in water. And so you actually can form a coordinate a bond with the water donating a pair of electrons. In this case, we have a metal ion surrounded by ammonia. And so ammonia can donate a pair of electrons to form that bond with the metal ion.
Ammonia also acts as a Lewis base toward metal ions, as in this example of the cobalt-3 hexamine complex. The ammonia electron pairs are donated into vacant metal orbitals.
And so a metal complex is a category of compounds. You have a metal and you have ligands around it. And so the metal is behaving like a Lewis acid because it's accepting electron pairs. The ligands, the things attached to it, are behaving like Lewis bases because it's donating electron pairs to form those bonds. Inside hemoglobin, you have a heme group with an iron, and it's a metal complex. Now, the way your blood transfers oxygen is by oxygen getting attached to the iron in the heme group. Now, that's just a Lewis acid-base reaction. Unfortunately, carbon monoxide is a stronger Lewis base than oxygen, and so you can die from carbon monoxide poisoning because the carbon monoxide can tie up the heme groups, and so no longer can the body transport oxygen.
Oxygen binds weakly to the iron ion at the center of a heme group in the hemoglobin molecule. In an oxygen-poor area of the body, the O2 is easily removed. Carbon monoxide, in contrast, binds very tightly to the iron and is very difficult to remove. The presence of carbon monoxide makes it impossible for the blood to transport oxygen effectively.
And so again, we can't use Bronsted theory to talk about this reaction because there's no transfer of hydrogen ions. We can use Lewis theory. And just like Bronsted theory, we can talk about which is a stronger Lewis acid, which is a stronger Lewis base. And so an interesting question to ask would be, in that top reaction, is ammonia behaving like a Bronsted acid, Bronsted base, Lewis acid, or Lewis base? And so if we look at it, we're going from ammonia plus a metal ion to a metal complex. And so ammonia is the ligand. It's going to behave like a Lewis base. It's donating its electron pair to form a bond with the metal ion. The metal ion is behaving like the Lewis acid. It's accepting that electron pair. Now down here, we have the same question. It's a little bit trickier. Notice that you do have a transfer of hydrogen ions. So ammonia is grabbing that hydrogen ion, forming the ammonium ion. And so we'd say that it's behaving like a Bronsted base. But it's doing that using a lone pair of electrons. And so in this reaction, we can use either Bronsted theory or Lewis theory to describe it. And we say that ammonia is behaving like both a Bronsted base and a Lewis base. And so hopefully you should be able to recognize, strong acids, why some acids are strong, why some acids are weak based on their structure. You should know how both Bronsted acids react and how Lewis acids react. I hope that helped.